All right, so we got this graph here, and it's y equals x cubed. And you've learned that graph before. Whenever we went through the parent functions, the first unit of this year, you learned what the x cubed graph was. And if you remember, that graph was kind of like a little, very vertical looking S or snake, as I like to call it, like a vertical looking snake. It'll be clear on the next slide why I think of this as a snake. But yeah, super vertical, upright looking curve. That's our shape. And let's recall some of the points that go along with this equation. So if we make our table here, our XY chart, and we just pull the original points, right? So the original points were -2 through +2. So those are our original points there. Okay, and then we apply them to this equation. So y equals x cubed. So what is 0 cubed? 0. And what is 1 cubed? 1. What is 2 cubed? Yes, 2 cubed is 8. 2 times 2 times 2. What is -1 cubed? Yes, -1. Okay, -1 times -1 times -1. Let's look at that. -1 times -1 is +1. And then times -1 again equals -1. So if I square -1, what happens to the negative? It goes away. But if I cube -1, what happens to the negative? It stays, okay? This happens as you continue to do higher and higher powers. Okay, to the 4th power, the negative goes away. To the 5th power, the negative stays. All of the odd powers retain their negative. And when you raise when you raise a negative to an even power, the negative goes away. So we see the same thing with -2. -2 times -2 times -2, right? That's -2 cubed. -2 times -2 is +4 times -2 equals -8. Okay? So -2 cubed is -8. And so if we graph those points, we have 0, 0, 1, 1, -1, 1, or -1, -1, I mean, 2, 8, and -2, -8. And that's how we get that really vertical looking curve. Vertical looking curve there. And then what's the domain of this graph? Yeah, it's -infinity to infinity, right? From left to right, this thing goes forever and ever. And I know it's weird because this arrow looks like it's going down, but it's also going to the left slightly. It's just really, really steep. And same thing with the arrow on top. It looks like it's going up, but it's also going to the right ever so slightly forever, and it's really, really steep. What is the range? How far up and down does this thing go? Yeah, -infinity to infinity, or we could say all real numbers if they didn't specifically ask for it in interval notation. Okay? So that's the x cubed graph, and we can stretch that and shift it around and reflect it in all of the same ways that we saw with square root graphs. And so you have some different transformations down here. And let's go ahead and walk through some of these. This top left corner here, x minus 3 cubed plus 2. So what's the plus 2 doing? Yeah, that's up 2. Any adding or subtracting at the end is always up and down. At the end is always up and down. And then we have a -3 with the x. -3 with the x. So changes that are with the x, they are right and left, and they're always opposite. So this -3 is right 3. Okay. So jump over to the far right, and here we have negative x cubed. Negative x cubed. What is the, first of all, does the 3 belong to the x, or does it also belong to the negative? In other words, is the negative with the x or not?
Not yet.
Who thinks with? Raise your hand. Who thinks it's with the x? Who thinks it's not with the x? Okay, the nots win. The nots win. Okay, this is not with the x. If it was with the x, it has to be in parentheses with the x. This is what with the x would look like. Okay? And remember, that makes the difference because all of the changes that are with the x are horizontal, right? And all the changes that are not with the x are vertical. Okay, so in our example here in the blue box, that negative is not in parentheses with the x, so that makes it vertical. This is a vertical what? Reflection. Reflection, right. So the negative gives us a reflection.
And if it was with, it would be a horizontal reflection?
Exactly. If it was with the x, like in parentheses, it would be a horizontal reflection. Okay, why don't you finish out listing out or describing the transformations that you see, and I'll do the same, and then you can check your answers. Hey, check your answers there when you're done. Any questions on those transformations? Feeling pretty good about that? Okay. Let's move on to this next graph here. On the next graph, we've got y equals cube root of x. Cube root of x. And I don't think you guys have seen this one before. This graph is going to make a similar kind of snake pattern, but it's going to be more horizontal, like that. And so you can see now why I think of it as a snake. This is like, I always imagine like a cobra with its head raised up, you know. So it makes that kind of shape. And then let's look at the parent function points. So x, y. And let's start with 0, 1, and -1. And then we'll think a little more about the other two in a minute. So y equals cube root of x. Okay, so the cube root, what is the cube root of 0? 0. Any root of 0 is 0. And what is the cube root of 1? 1. Good. What is the cube root of -1? You sure? -1, +1. Let's imagine here for a second. So we're asking, when we ask what is the cube root, we're asking, tell me a number that when multiplied by itself and by itself again would give me -1. So 1 times 1 times 1 would give me +1. -1 times -1 times -1 would give me -1. And so the cube root of -1 is -1. Okay?
Why did you make us so unsure?
I don't want you to read my face and just try to guess what the answer is. I want you to be confident in what math you know. And then the next number would be 2, right? But do you know, off top of your head, what the cube root of 2 is? Yeah, a number times itself again that gives you 2. It's this terrible decimal. Okay, we don't know it. Nor do we know 3 Or even 4. We don't know what the cube root of 4 is. We know what the square root of 4 is, but that's not cube root. It's not the same thing. We don't know what the cube root of any of those numbers is until what? What's the next cube root we know? 8. We know 8. We know 8. Okay, and what is the cube root of 8?
2.
Yeah, 2. So we have to skip all the way to 8. Just like when we were doing the square root graph, we had to skip to the square roots we knew. Same idea here. And if we know the square root or the cube root of positive 8, we also know the cube root of negative 8. What is the cube root of negative 8? Negative 2, right? Negative 2 times negative 2 times negative 2 is negative 8. So that's how we get our parent function table, by taking the cube root of those x values. And let's plot that, and we can see our kind of snake curve happening. 0, 0. 0, 0 there. 1, 1. Negative 1, negative 1. But instead of going super steep, we're going 8, 2, and negative 8, negative 2. Negative 8, negative 2. So we can graph that. Okay. And those two curves continue to go. Obviously, they're going right and left forever and ever, but they're also going up and down forever and ever. Okay. So our domain is negative infinity to infinity, and our range is negative infinity to infinity. Okay, and then let's look at some of these transformations. So I think you already can do the top two transformations on your own. One of the plus 5s is with the x, and the other one is not, right? It's not underneath the root, so that means it's not with the x. So why don't you jot down, describe those transformations, those top two at least. The one on the left there is left 2, right? It's right and left because it's with the x. And we decided on left.
Did you mean to say
Yeah, I meant to say 5, sorry. I wrote it. Left 5, so it's left because it's opposite, right? And then up 5 on the other one, up 5. And then, excuse me. We have a multiplier here on the last examples. So we have a 5 that's multiplying outside of the x and a 5 that's multiplying inside with the x. So let's start with the easier one, outside the x. What is that 5 doing? Vertical stretch, very good. Vertical stretch with a scale factor of, we would say a factor of 5, meaning it's 5 times. The height of that graph would be 5 times higher than normal. And then if that one's a vertical stretch, because it's on the outside, this 5 that's on the inside would be what? It would be a horizontal, and everything with the x is backwards. So it's a horizontal what? Yeah, compression. A horizontal compression. It's always opposite with the x. And we would say it's a factor of 1/5, meaning all of those, this graph's distance from the axis is going to be reduced down to 1/5 of what it was before. It's going to be squeezed in toward the axis, compressed in. Okay. So that's how you can describe those transformations. There's some of that in the homework. Just use your words to describe the transformation. All right. Okay, let's do some graphing. So here we go. Our instructions are to graph, find the inverse, and graph the inverse. So go ahead and start by just graphing it. you've got a x cubed that's been shifted. And how has this been shifted? Yeah. Down 1, down 1. So go ahead and graph that, and I'll graph it, and you can compare your graph to mine. Hey, so there is my graph. You see the blue dots there those are the original, the parent function dots, and then I shifted them down 1. I shifted each of those dots down 1. Okay. And just for grading purposes, just so you know, I'm looking here in the middle. When I'm grading a quiz or a test, and I'm trying to decide, does this student actually know what they're doing? I'm looking at this. Did they make it obvious that these 3 dots have shifted down from where they normally are? Okay? So as you're working on your stuff, just make sure that you're making that clear for me. And then I'm less worried about these other dots. They should be, try to make them right, but it's a little harder to make the curve right there. Okay. In fact, this one is wrong. That should be only down 1, not 2. Like that. Okay. So that's the original function. And step 2, they asked us to also find the inverse. Find the inverse. So I'm going to go ahead and work on finding the inverse. How do you find the inverse? Yeah, y equals x cubed minus 1. And so switch x and y. Switch x and y. So this is inverse. This is the work of finding the inverse. So x equals y cubed minus 1. Don't switch the cubed. That's not part of the x or the y. Leave the cubed where it's at. Just switch x and y, and then get y alone. Let's go. So we're going to add 1. X plus 1 equals y cubed. And then how do I get rid of y cubed? Yeah, how do I get rid of cubed? I get rid of cubed with cube root. Cube root. Okay? And the cube root goes over that entire side. X plus 1. All of it is under the cube root. So I'm cube rooting the entire, both sides. And I get y equals cube root of x plus 1. So my inverse, I could say that this is kind of how we write y equals for inverses. F inverse of x is cube root of x plus 1. No, I'm not worried about that, especially if on your graph you've labeled which one's the inverse, or you wrote the equation in the space that I provided when I told you to give me the inverse. But I just don't want you to get thrown off if you see resources or future maths that write it this way. That just means inverse, or final exams, or whatever. Okay?
Wait, wouldn't the minus 1 be after the parentheses, 6 parentheses?
No. Nope. F inverse of x. That's how they write it. Okay. And then we can graph this, okay? This is a cube root function that's been shifted. Which direction? This inverse, yeah. Left 1, okay? All right, it's with the x, so it's right or left. And we said left because it's opposite. So that's a cube root that's been shifted left 1. So here are your cube root original dots, okay? And then they're shifting that left 1. Each of those is going to the left 1.
Bless you. Bless you.
Caroline, bless you. And there is our inverse graph. Okay? So you see x cubed and cube root of x, they're inverses of each other. And are either one of those graphs like half of a curve? You know, like the square root graph was like half of the curve. Do we see that happening here? No. Both the cube root graph, the horizontal looking one, and the cubed graph, the vertical looking one, both of them are going forever and ever, right and left, forever and ever, up and down. So are we going to have to restrict the domain on these? No, we only had to do that whenever we had to make the inverse match the original. And right here, automatically, when we graph the inverse and the original, we see that they look like perfect mirror images. Remember, they should always look like a nice mirror image across that diagonal. You don't have to graph the diagonal. I just want you to see that. They should always look like nice mirrors across that diagonal there, y equals x. Okay. Any questions on this one? All right. Let's go to the next one. Why don't you try the next one? Try it on your own. Start to finish. Graph, find the inverse, and graph the inverse. And we'll see how you do. I'll put my answer up in a little bit. Okay, so there's my original in blue, the original function. And then I've done some inverse work here. All right, to get rid of the cubed, I have to cube root. To cube root there, and that cancels out the cubed. And then I have to add the 1. And because I added the 1 after I cube rooted, look, that 1 is not underneath the root. It's not the cube root of x plus 1. It's the cube root of x and then plus 1. All right, the 1 is not underneath the root because I added it after I cube rooted. Okay, and what difference does that make, Matt? As opposed to
going left.
Yeah, if it was underneath the root, it would be going sideways. But since it's not, since it's outside of the root, it makes it go up. So that does make a difference. Make sure you get that right. Very good, Matt. So y equals cube root of x plus 1. And we can graph that. That's a cube root function, so that's kind of the flatter looking snake. And it's been shifted up 1. So there are my points.
How do you know when you're supposed to, do you always cube root it before you move the number? Because you didn't do that last.
It depends. It depends. If the entire, in this one, the entire thing on this side was being raised to the third power. And so I could do nothing until I got rid of that third power because everything was being raised to it. So the first thing I had to do was cube root it away. On the previous example, that was not true. The cube root was not the thing being cubed was not consuming this whole side. So I moved the 1 first, and then I cube rooted. Okay, good question. So again, those are our inverse and original graphs. All right, they are mirror images of each other across that diagonal line. Okay. If you're feeling good, try the next one. Y equals negative 2x cubed. And remember how we graphed when there was a multiplier. Same rules as in the last unit. Give it a shot. Hey, check some of your work there before you get too far. So that negative 2, that is not with the x. Right? That's not with the x. If it was with the x, it would be in parentheses with the x. Okay, so just because it's right next to the x doesn't mean we think that it's with the x. Don't get fooled by that. Things that are with the x are like, they're like in some kind of box with the x. They're in parentheses with the x. The equation has gone above and beyond to make it obvious that that's with the x. This one is not. Okay, so since it's not with the x, we multiply it to the y values. That negative 2 times the y values. And then keep in mind your sign rules. What is negative times negative?
Positive.
Positive. So negative 8 times negative 2 is positive 16. And then keep track of all of your sign rules there. Positive times negative is negative. And then cross out your old points so you don't get confused. So negative 2, 16, it's like off the charts. I'm not that worried about that one. But what I want to make really obvious for Mr. Wagner is that those central points are where they should be. Okay, so we see that reflection, that vertical reflection happened, right? This curve is still really steep up and down, but it's even steeper because of the stretch, and that negative reflection made it go the opposite direction. So instead of, like from left to right, instead of starting low and ending high, it starts up high and then ends down low. So that's our original graph. And then to find, they just told us the graph, so we'll just leave it at that. Any questions on this? How do we feel about this? 1 to 5, how do we feel? I see everybody's hand. Awesome. All right. All right, cool. Let's do one more then. Let's do this one. Yeah, graph, find the inverse, and graph the inverse. All 3 steps there. Do this last one. If we feel good about this one, then we'll be done for our notes. All right, so there is my original function. The blue dots were the parent function, and then I shifted them all down 2. Okay, down 2. That negative 2 is down 2. So that's step 1, to graph the original function. And then step 2, find the inverse and graph the inverse. Is that my computer?
No, it was me.
All right, so I am switching x and y. To find the inverse, I'm switching x and y. And I see that I've got a cube root. And maybe by now I know, how do I get rid of that cube root?
Cube it.
Cube it, right? Cube it. But can I cube this right away? Why not? Yeah, I don't want to cube it right away unless the thing that's being cube rooted is the only thing on that side. All right? I don't cube this cube root away until the 2 is gone. In other words, until that's the cube root thing is isolated, the only thing on its side. And now I can cube it to take that away. And it's very important. I'm cubing the entire left side. The entire x plus 2 is being cubed. It's being cubed. So y equals x plus 2 cubed. And what difference does that make, Alex? Why should I care if the whole thing is being cubed or not?
I don't know.
What do you think, Caroline?
Like
Yeah, like as opposed to just the x being cubed.
Oh, then you have to.
Oh.
We have to cube the 2 as well, so you make it 8 and go up 8 or left 8, right?
What do you think, Alex?
When the thing is like cubed like that?
Yeah, like why does it make a difference that I'm cubing this whole side, this whole x plus 2, as opposed to just putting that cubed on the x part?
Because now it's like you have 2 of those. I mean 3 of those things.
Yeah. What do you think?
I don't know.
Ryan?
Well, because if you just keep the x, it'd be up to, not left.
Yeah, if I just put it on the x, like that,
Oh.
well, that would be up to. That would be up to,
I did see.
right? So I need it to be, it's the whole side cubed,
So it's kind of-
right? So I would have gotten that wrong. I would have said that it's up to instead of, which direction would this be? Left to, right? Left to. Sorry, I was asking a good question in a terrible way.
Yes.
Okay, well, you didn't have to agree that wholeheartedly.
Sorry.
Feedback.
Feedback. It's helpful, even though it hurts.
The truth hurts sometimes.
Nah, I can take it.
That's hard.
Whoa. Okay, so there's our inverse. There's our inverse there. It kind of makes a cool design when you graph them both together. Okay. How do we feel about this? 1 to 5. How are we doing? Everybody's hand, 1 to 5. Okay.
Or the last one, right?
I don't see everyone's hand yet. I don't see everyone's hand yet. Everybody's hand. Okay. All right. We can be done. I think we've got enough confidence in the room that we can be done. Your homework is on Canvas, worksheet number 1.